Okay, so this is the review session for EGME 417, spring semester 2021 for the first midterm. Okay, so I took a look at the poll that's on Canvas, and these are the top 3 choices. And so it looks like everyone wants to see some more 2D stuff. And so the leading candidate was 2D diffusion, and the second one was 2D convection diffusion. And then finally, if I have time at the end, maybe after about an hour, I'll do convection diffusion. Okay. All right. And so let's go ahead and start with 2D diffusion, right? And so the 2D diffusion equation was given by this one right here, okay? And so we had K times d squared phi dx squared plus d squared phi dy squared is equal to our source function q of xy, okay? Okay. And so in order to solve this equation, at least with finite differences, what we had to do was we had to apply our finite difference scheme to both of these derivatives right here, okay? Because remember, the ultimate goal for any finite difference scheme or any computational scheme in general is to take a differential equation and then convert it into a set of algebraic equations, okay? Okay. And for the midterm exam, this is all that I'm going to be expecting you to do. Okay. I know for the 2D problems, the the MATLAB code for those gets a little bit complicated because there's a lot of things going on. But what you'll see in this review today that, for the midterm exam, all I'm going to expect you to do is to, take a differential equation, discretize it using finite elements, and then come up with a set of algebraic equations. Okay. Okay. And so, let's go ahead and apply finite differences to this. Right? And so I'm going to apply our usual central difference scheme for our second order diffusion derivatives to each of these guys. Right? So we have k. Right? First, we have d squared phi dx squared, and so that's going to be phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j all divided by delta x squared, okay, plus, now we have d squared phi dy squared. So you have phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1 all divided by delta y squared, okay? And this is equal to q I j, okay? I comma j. Okay. So it's basically going to be our source term evaluated at, the I comma j coordinates, okay? All right. And so what we usually do at this point, because this expression right here is a little bit difficult to work with. And so what we want to do is we want to simplify this, by first of all by doing some assumptions, but also by manipulating this algebraically. Okay. And so first, let's assume that our grid spacing is the same in the x and y directions. Okay. And let's say that the grid spacing is going to be delta. Okay. And then let's make it so that the left-hand side of the equation is free of coefficients, and we kind of move everything to the right. Okay, and so that means that we're going to move our diffusion coefficient k over to the right-hand side, and we're going to move our grid spacing over there as well. Okay, and then once we do that, we can take these two terms, because both of these are the same, phi ij, which is the phi value at this at this node, and then we can combine them into one term. Okay. And so in the end, what we get is the following. Right? And so we get phi I plus 1 comma j plus phi I minus 1 comma j plus phi I j plus 1 plus phi I j minus 1 minus 4 phi I comma j is equal to q I comma j times delta squared, all divided by k. Right? And this right here, this is our finite difference equation for 2D diffusion. And so what you would want to do is you would want to take this equation here and apply it to the different nodes in your grid or in your in your domain, and then from that you'll be able to get a set of algebraic equations. Okay. All right. And so let's examine this this expression here a little bit, because right now what we have is 5 different phi values here, right? Okay. And so we're going to have, this is the first one, this is the second one, this is the third one, this is the fourth one, and this is the fifth one. Okay. And all of them are either either I comma j or I comma j's immediate neighbors. Okay. And so if you remember, in class, what we did is we drew this what I call the stencil. Which is basically this cross formation where the center of this cross is going to be I comma j. Okay, so that's the node that we're applying this to. Then we have its upper neighbor, so its upper neighbor is I comma j plus 1. Okay. Next is I j minus 1. Then we have I plus 1 comma j, and then I minus 1 comma j. Okay. Right. And so those are all the neighboring nodes in terms of their ij coordinates. But usually, just for the sake of simplicity, what I like to do is I like to label these with kind of better names. Okay. And so this this node at I comma j plus 1, this is going to be our top neighbor. Okay. The one at I plus 1 comma j, this is going to be our right neighbor. Okay. The one at I comma j minus 1, this is going to be our bottom neighbor. And the one at I minus 1 comma j, this is going to be our left neighbor. Okay. And so what you can do is you can, just kind of for the sake of writing out equations by hand, you can kind of replace these I and j coordinates in this expression here with, where those things are located, right? And so first here we have I comma j, and so this was our right neighbor. Okay. Then we have I minus 1 comma j, and so this was our left neighbor. Okay. Then what we have is I comma j plus 1. And so this is obviously our top neighbor. Then we have I comma j minus 1. And so this is our bottom neighbor. Okay. Okay. And then I comma j, that's just the node that we're applying it to. So, it's not a neighbor. It's our own house in this case. Okay. Okay. And so I know in the class we spent a lot of time talking about ID numbers and how to obtain those ID numbers and things like that. But for this exam, let me kind of show you an example of what I would expect you to do on the exam for these kinds of problems. Okay. And so let me actually take the example that we did in class and then show you basically how this problem would look like on the exam. Okay. Okay. All right. So in this example, we're going to solve this equation right here. Right. Okay. And so we're going to have d squared phi dx squared plus d squared phi dy squared. Actually, let's change it up a little bit just because this one didn't have a diffusion coefficient. And so let's say that we have a diffusion coefficient of 6 out here, okay? And then this is going to be equal to 3xy, okay? All right. And usually, with these problems, I'm going to give you the grid that you're going to be solving it on, right? Right. And so, just for the sake of the exam, I'm just going to give you guys square grids, right? So no weird stuff. Right, so let me label all these nodes. Right? And so the fact that, I'm going to be labeling the nodes for you, you don't have to worry about the ID equation at all, okay? Okay, so in this case, we have 16 nodes. We have 4 nodes in each direction, okay? All right, usually what's going to be given to you is going to be the, the grid spacing. Okay. And so in this particular case, let's just assume that our grid spacing, since I don't think I gave you one in the homework, in the in-class example, let's say that our grid spacing here was 1/4. And so let's say our grid spacing is 0.25, okay? And so that tells us that, in between each node in the X and Y direction, we're going to have 0.25. And we can say meters or something like that, right? Okay. Where node number 1 here is the origin. So we assume here, usually we assume that node number 1 is always at the origin. Okay. Okay. And so, in an in-class or on the exam, I would give you a problem like this with with a grid and the equation and the grid spacing. And what I would want you to do is I would want you to find out or write down or derive all the algebraic equations that are needed to find a finite difference solution. Sorry, finite difference. I'm teaching several classes this semester with very similar names. Okay. And so, what you should have is you should basically come up with, one equation per node here, with the exception of the corner nodes. And so for the corner nodes, we can neglect those because we don't really need those, okay? And so in this example here, we're going to have 12 equations that we need to solve for, okay? 4 of these are going to be on the interior, and then the other 8 are going to be on the boundary, okay? Okay, so for this problem, need 12 equations. Okay. And so you can go about this, in several different ways. Just because I did the finite difference equation on the previous page, let's start with the interior nodes and let's take this differential equation and let's discretize it with finite elements and apply it to, all our interior nodes. And so you can see here, we have 4 interior nodes. And so these are interior nodes here that I'm going to circle in blue. Okay. And the reason, I call them interior nodes is because they have neighbors on every side of them, right? And so if we look at node number 6, it has neighbors 5, neighbors 2, neighbor 7, and neighbor 10, right? And so in order for us to be able to apply this finite difference scheme here, it needs to have 4 different neighbors, and node number 6 satisfies this criteria. Okay. Then there's node number 7, and so node number 7 obviously has, it's 4 neighbors too, right? And same thing for 10 and 11. Okay. But for the nodes on the boundary, these are missing at least one neighbor, and so we wouldn't be able to apply those, that finite difference solution. Right? And so some examples of the boundary nodes will be like nodes number 14 and 15. And so since both of these are on the top of the domain, they're missing a top neighbor. And then like nodes 5 and 9, these are missing a left neighbor. Nodes 8 and 12, they're missing a right neighbor. And 2 and 3, those are missing a bottom neighbor, right? And so for those boundary nodes, what you're going to need to do is you're going to need to apply some boundary conditions on there, which I've neglected to give you at this point. So let me go ahead and remind you what the boundary conditions are. Okay. And so the boundary conditions, they're going to depend on your problem. And so, I'm going to give you the boundary conditions for this problem, but when you're doing this on the exam or, and for the homeworks or anything like that, you have to really pay attention to what boundary conditions are given to you and then adjust the problem or adjust your equations to account for those boundary conditions. Okay. And so for this problem, on the bottom, actually, let me change these up a little bit just to give you a slightly different look. Okay. So I think in class we did actually derive these equations. Okay. Let me just double check real quick. Oh, actually, we didn't. Okay, so let me keep the boundary conditions the same for this case, and I'll just show you how it is. But again, remember, these boundary conditions are only specific to this problem, and so you want to make sure that you look at the problem and see what boundary conditions are being applied. Okay, so on the bottom boundary here, we'll have a Dirichlet boundary condition of 25. On the left side here, we'll have a Dirichlet condition of 50. Okay. On the top here, we can say we'll have a Neumann condition of 10. And then on the right here, we'll have a Neumann condition of 0. Okay. All right. And so for each of the boundary nodes that I've circled in orange, we're going to apply an equation that corresponds to that boundary condition. Okay. Okay, so let's go ahead and start this up. So let's start with the interior nodes first. Okay, and so for the interior nodes, we're going to basically apply the finite difference scheme that we applied previously. All right. And so just to kind of remind you, let's go ahead and derive the the finite difference scheme for this equation here. And so our differential equation was 6 times partial squared phi partial x squared plus partial squared phi partial y squared is equal to 3xy. Okay. Right. And so let's go ahead and plug in the finite difference representations for these derivatives into this expression here. Okay. Okay. And so we have 6 out in front here. And then first, let's do the x derivative. And so the x derivative, we're going to have phi I plus 1, comma j, minus 2 phi I, comma j, plus phi I minus 1, comma j, all divided by delta x squared, okay, plus the y derivative, which is phi I j plus 1 minus 2 phi I, comma j, plus phi I j minus 1 all over delta y squared. Okay. And this is equal to 3xi y j. Okay. All right. And so let's go ahead and plug in the numbers at this point because we have everything that we need, right? And so, from the previous page, we basically said that delta here is going to be 25 or 0.25. And so this will be delta x, delta y is equal to 0.25. Okay. And so when we plug that in and then factor it out, what we get on the left-hand side is 6 divided by 0.25 squared. And so that's going to be, pull out my handy dandy calculator, 0.25 squared, 6 divided by the answer, 96. Okay. And so we're going to have 96. Okay. Phi I plus 1, comma j. Okay. So I'm going to go ahead and combine, the phi I, comma j terms. Phi I j plus 1 plus phi I j minus 1 minus 4 phi I comma j. Okay. And this is equal to 3x I y j. Okay. And so let's go ahead and divide both sides by 96, and then we'll have our finite difference equation for all of the interior nodes. Okay. Okay. And so we're going to have phi I plus 1 comma j plus phi I minus 1 comma j plus phi I comma j plus 1 plus phi I j minus 1 minus 4 phi I comma j, right, is equal to 3 divided by 96. So go ahead and compute that that decimal. And so this is going to be 0.03125 xi yj. Okay. Right. And so this right here, this is the finite difference equation that we can apply for the interior nodes. Okay. And so for all the nodes that I've circled as interior there, so the ones that are circled in blue, we can apply this equation to it. Okay. And just like we did previously, let's go ahead and replace these I and j components here. And let's replace them with kind of names that are going to be a bit more useful for us. Okay. And so I plus 1 comma j, this is the right neighbor. Okay. I minus 1 comma j, this is going to be the left neighbor. Then we have the top, then we have the bottom, and then we have me. Okay. Okay. And so now let's take this equation and now let's apply it to all of the interior nodes in our grid. And so essentially, what you're doing in these kinds of problems is you're basically mimicking what MATLAB would do, in these situations. Because normally, in MATLAB, what we're doing is we're building up the left-hand side matrix and the right-hand side vector. We're doing this with loops and with assignments and all that stuff. What I want you guys to show on the exam is that you understand kind of, not just, what code to write, but you understand what the code is actually doing. And the way that I'm going to assess that is basically I want you to kind of replicate those same steps, but with hand calculations. Okay. And so we have four interior nodes, sorry. And so let's apply them. So let's start with node number 6. Okay. And so for node number 6, we have our right neighbor, and so the right neighbor for node number 6 is going to be phi 7. Okay. Then we have the left neighbor, and so the left neighbor for node 6 is going to be phi 5. Then we have the top neighbor for node number 6, which is going to be phi 10. Then we have the bottom neighbor, which is phi 2. Okay. Then we have minus phi me, which is going to be 4. Sorry, minus 4 times phi 6. Okay. And then we multiply by the right-hand side of the equation. So on the right-hand side, we have 0.03125, okay, times xi and yj, okay? All right, and so xi and yj, remember, these are the physical x and y coordinates for those nodes, okay? Okay. And so the physical x coordinate for this, assuming that node number 1 is at the origin, this is basically at node I is equal to 2 and j is equal to 2. Okay. And so, let's do this. Okay. And so the ij for this node is equal to 2, 2. Okay. And so that tells us that xi and yj for this, considering that the node spacing here is 0.25, and so since we're at 2, 2, we're going to move over one space in the x direction and one space in the y direction. That means this is going to be 0.25 and 0.25. Okay, so go ahead and plug those in. Okay. And so we can finally then write the last of the equation. And so we have phi7 plus phi5 plus phi10 plus phi2 minus 4 phi6 is equal to 0.303125 times 0.25 squared. And so let me go compute that. Okay. And what we have is 0.002 about. And so that's our first algebraic equation for this problem, and that's for interior node number 6. Okay, and so let's do the next interior node, which is node number 7. Okay, and so node number 7, we're going to apply the same thing, and so we're going to apply the right neighbor. And so the right neighbor for node number 7 would be phi8 plus the left neighbor, which is phi6, plus the top neighbor, which is phi11, plus the bottom neighbor, which is phi3, minus 4 times phi me, which is phi7, okay, is equal to 0.03125 multiplied by xi and yj, right? And so for node number 7, the ij coordinates for this is going to be 3, 2, right? Because it's basically three nodes over in the right direction, and then one, and then 2 nodes up. Okay. And so the physical xy coordinates for this are going to be, assuming our grid spacing 0.25, it's going to be 0.5 and 0.25. Okay. Right. And so actually, let me label that here just so you know, right? And so since this node in the origin here, this is going to be at 0, 0. Right. This first node right here, node number 6, this is going to be at 0.25, 0.25. Okay. And then the physical coordinates for node number 7 here is going to be 0.5, 0.25. Okay. And then we'll use that same scheme for, nodes number 10 and 11, right? Okay. And so this is going to be times 0.5 times 0.25, right? And so the final equation for node number 7 is we're going to have phi8 plus phi6 plus phi11 plus phi3 minus 4 times phi7 is equal to, this is going to be approximately double that, and so it's going to be 0.004. Okay. And there's the second equation out of 12 that we need. Okay. Okay. And so for node 10 and 11, those are going to be more or less the same thing. So let me go ahead and just kind of speed right through those, just so that we can get to the boundary conditions. All right. And so node number 10, let me start out by writing its coordinates, right? Right. So its ij is going to be 2, 3. And so this tells us that the x and y is going to be 0.25, 0.5. Okay. And then from here, we can write out all the phi values. Okay. And so first we have the left neighbor, so it's going to be phi9, then the right neighbor, which is phi11, then the top neighbor, which is phi14, plus the bottom neighbor, which is phi6, okay, minus 4 times phi10, right? And this is equal to 0.03125, times 0.25 times 0.5, and so that's going to be approximately the same. It's going to be 0.04, okay? And remember, for these neighboring nodes right here, you want to look at the original grid here and see, what the left, top, and right neighbors are for this, okay? And so we just did node 10. And so we're going to draw kind of our stencil around that way, just like that, okay? And so you can see here from this diagram here that, starting at node 10, the left neighbor to this is going to be node 9. The neighbor on the right is going to be node 11. The neighbor on the top is node 14. And the neighbor on the bottom here, which is kind of covered by this line now, is node number 6. Okay. And that's how I kind of pulled out these numbers here on this thread. So we can box this. And then finally, let's do node number 11. That's the last of the interior nodes. Okay. And so node number 11, this coordinates for this is 3, 3. In terms of xy, this is going to be 0.5 and 0.5. Okay. And then so let's go ahead and write out our equation. And so the left neighbor for node number 11 is phi 10. Okay. Then we have the right neighbor, which is phi 12. And the top neighbor, which is phi 15. Then the bottom neighbor, which is phi 7 minus 4 times phi 11 is equal to 3 divided by 96 times 0.5 squared. And so that's going to be about 0.008 because it's going to be approximately double what that was. Okay. And so that's our first 4 equations. And so those are for all the interior nodes. But we still have 8 more to go because the problem is not complete until we find out all of the algebraic equations, for all the nodes in the grid. Okay, and so let's do the other 8 nodes now. And since all the other 8 nodes are on the boundary, their equations are going to be governed by the boundary conditions. Okay. And so, for the boundary conditions, we don't actually use, the finite difference scheme for that. We just apply whatever boundary condition is there. Okay. Okay. And so let's start with the left and the bottom boundaries because those are relatively simple because those are Dirichlet. Okay. And because remember, for Dirichlet boundary conditions, we're just directly specifying the solution at the node. Okay. All right. And so for the bottom boundary here, let's start with the bottom one because that's the lowest node numbers. Okay. And so on the bottom, if we go back to our diagram, okay, on the bottom here, you can see we have 2 nodes that we need to worry about. Because remember, we're ignoring the corner nodes because those don't really matter. And so on the bottom boundary, we can set the equations for node number 2 and node number 3. Okay. All right. And so on the bottom here, what we have is we need an equation for phi 2, an equation for phi 3. Okay. And since the a Dirichlet boundary condition is specified here, we can just apply the Dirichlet value, right? And so for this bottom boundary, if you go back to our diagram, we can see that the Dirichlet value that we specify here is 25, okay? And so that tells us that the solution has to be 25 for the nodes on that bottom boundary. Okay, and so what we have is phi2 is equal to 25, and then phi3 is equal to 25 as well. Okay. And just like that, we have our two more equations, right? So we have 6 equations down. So we have our 4 interior nodes and 2 nodes on the boundary, and then we have 6 more to go, right? And so let's continue this forward, and let's do the left boundary. And so for the left boundary, what we have is nodes number 5 and node number 9. Okay. And so we're going to have an equation for phi5, and we're going to have an equation for phi9 as well. Okay. And so according to our original diagram, okay, what we see for these nodes is that their Dirichlet value here is 50. Okay. And so what that tells us is that the solutions at nodes 5 and 9, and so phi5 and phi9, these have to be 50 right here. Okay. Okay. And just like that, we have 2 more equations. Right? And so from here, we just have, the top and the right boundaries left. And so these guys are Neumann boundaries. Okay. And so for Neumann boundary conditions, remember in 2D, we have to be a little bit careful about how we actually apply this derivative, right? Because Neumann boundary conditions, the way that we define them is that these are constraints on the derivatives itself, on the derivatives of the function. And what's unique about this, for 2D cases, is that the derivative is always taken in the direction normal to the boundary. Okay. And so let's start with the top. Let's start with the top boundary then. Okay. And so let me draw the top boundary here, or at least part of it, just so that you can get a glimpse of it. Okay. Okay. And so all I did was I just kind of took the 4 nodes that are on the top boundary and I just kind of replicated them here. Okay. And just because we're going to need them for the derivatives, let me add the next row too. Okay. Okay. And so from our diagram, what we had was that the Neumann boundary condition up here was equal to 10, right? And so that tells us that the derivative of the solution on this boundary has to equal to 10. Okay. And since we're on the top boundary right here, which is a horizontal one, the direction normal to this is going to be in the y direction. Okay. And so what we can do is we can kind of easily replace this, d phi dn with a d phi dy. Okay. And so that tells us that the derivative of the solution in the y direction has to be 10 for these guys. Okay. And we'll once again ignore the corner nodes. Okay. And so usually the convention that we choose for these derivatives is we take a finite difference scheme and we take a finite difference between the boundary node and also the node that's on the interior. Okay. Oops. Got ahead of myself. Right. And so what we do is we take a difference in phi values between, the inner neighbor or the node that's right on the interior of the boundary. And we subtract that from the phi value at the boundary. We divide it by the distance between them. Right. And so here the delta is going to be this distance here. Okay. And then that equals to whatever our Neumann value is. Okay. And so let's take this information and let's apply this equation to node number 14, which is our first, Neumann boundary here. Okay. And so for node number 14, the boundary node for this is obviously going to be 14. Okay. And so we're going to have a minus phi 14, right? And then in order to apply the, the inner one, we have to look at its immediate inner neighbor that goes away from the boundary. Okay. And so since the boundary is kind of shown by this line right here, its immediate neighbor right next to it, in the direction perpendicular to that is phi 10. Okay. And so we have phi 10 minus phi 14 is equal to, 10. And then we're going to divide this by the grid spacing, where the grid spacing here is 0.25. Okay. And if we simplify this, we can get our, boundary equation for this node. And so we have phi 10 minus phi 14, okay, is equal to, or I'm going to move the 0.25 over to the other side. And so we have 0.25 times 10. And so this is equal to 2.5. Okay. And just like that, we now have another algebraic equation for this boundary node. And we can do the exact same thing for node number 15. Okay. Okay, and so for 15, the boundary node for this is obviously phi 15, and the inner node for this is going to be phi 11. And so let's go ahead and apply those. And so we have phi 11, which is the inner neighbor, minus phi 15, which is the boundary node, divided by delta is equal to 10. Okay. If we simplify this, what we get is phi 11 minus phi 15 is equal to 10 times delta, and so this is 2.5. Okay. And so that's for the top boundary. And then we have one boundary left here, which is the right boundary. Okay. And so for the right boundary, what we have here is our Neumann conditions equal to 0. Okay. And so let me draw our right boundary here again. Okay, so our boundary nodes are 4, 8, 12, 16, and then the immediate neighbors are 3, 7, 11, and 15. Okay. Once again, we're going to ignore the corner nodes, and so we only need to write equations for node 12 and node 8. Okay. And then our boundary condition here was a derivative of 0. Okay, and so let's start with node 12. And so the inner neighbor for node 12 is going to be phi 11. Then we have phi 12, and this is equal to 0, right? We have delta there, but because it's equal to 0, we can just multiply delta by both sides. It's going to cancel out. Okay. And then we have the equation for phi 8, and so it's going to be phi 7 minus phi 8 is equal to 0. And those are all of our equations. Okay. And so with that, that's everything for this problem. Okay. And so just to summarize, when you're given these 2D diffusion problems, and this method works for convection as well. Okay. What you need to do is you need to take your original equation here, apply finite differences to it in order to get the kind of the generic finite difference scheme, which I've shown here on the bottom. Then what you're going to do is you're going to take this finite difference scheme, apply it to all of your interior nodes, and that will give you, all the algebraic equations for that. And then for all the boundary nodes, you're going to apply a specific equation for those that corresponds to their boundary conditions. Okay. Okay. And so it's a lot of writing, and so it's a lot of equations. So I realize that, but hopefully this kind of this kind of algorithm here is just kind of systematic, right? Or this process is systematic. So you go from equation, finite difference scheme, interior nodes, boundary conditions, boundary node equations, and then you're kind of done. Okay. And so that's 2D diffusion. And so let me add, let's go ahead and modify this equation here, or modify this example to include convection, because that was the other, that was the other thing that people wanted to see. All right, and so I'm going to take the same example, but I'm just going to add some convection to it. Okay? And so this example, we had 6. Okay. And so that was our diffusion term. And let's add some convection here, right? And so let me do something real quick. So let's see, 2 divided by 6. Okay, and so let's have a convection velocity of 90 in the x direction, right? So we have 90 d phi dx plus, and then we'll have a convection velocity of 6 in the y direction, okay, plus 3xy. Okay. And so now, this is the exact same example that we did, previously, but now what we have here are convection terms. Okay. And so, in addition to the diffusion derivatives, we're going to have to discretize these convection derivatives, with the finite difference scheme. Okay. And let's assume that we're working with the same grid. Just because I just went over the boundary condition nodes in kind of excruciating detail. So I don't want to repeat that. But when you add convection to this, it's gonna change how you discretize the interior nodes, because now our equation here is is different. Okay, so let's label all of these nodes. Okay. And so, what these convection terms are going to do is they're going to change, how we write the equations for all of these nodes right here. Okay. Okay. And so the first decision you're going to have to make is which finite difference scheme are you going to pick for the convection derivatives? And actually, to make this interesting, let's make this a minus 90. Okay. Because remember, for second order derivatives, generally we only just have one option for that. And so we just have the central difference scheme for the diffusion derivatives. First of all, because they're accurate and they're simple. And second of all, because diffusion, remember what diffusion physically is a passive spreading of some material across a space. Okay. And so since diffusion doesn't really pick a direction, it just kind of goes equally in everywhere. We can use a central difference scheme for this, and it works out just great for that. Okay, but for the convection terms, remember convection, as a process means the active transport of a material through a fluid field. Okay, and so what's happening here is there's basically a fluid, be it air or be it water, that's kind of actively pushing the the quantity phi throughout our domain. Okay. And so because of that, what can happen sometimes is, the system can be unstable if we pick a central difference scheme. Okay. Right. Right. And so our two options here are you can either pick central difference. Okay. And the nice thing about central difference is that if the solution is stable, This leads to the most accuracy. And then the other option here is some kind of upwinding scheme. Okay. And that's either using forward difference or backward difference, depending on which direction the velocity is coming from. Okay. And the nice thing about upwinding is that it's always stable. Okay. But remember, upwinding schemes, be it forward difference or backward difference, are they're not as accurate. Okay. Right. And so, in general, what we would prefer is we would actually prefer to use a central difference scheme because that leads to a more accurate solution. But the caveat here is, if stable. Okay? And the way that we check whether, a central difference scheme will be stable or not is that we check the Peclet number. Okay. And so let me do that on the next page so that we can decide what we want to do with these convection derivatives. Okay. And so in 2D, you have the added complexity where you need to compute Peclet number in the X and the Y direction. Okay. And so Peclet in the X direction is going to be U times delta X divided by K. Okay. And what our stability criterion basically says that, if we compute the Peclet number, then the Peclet number should be less than 2 in order to get a stable solution. Okay. And so let's go ahead and plug in the values for these from the previous exam or the previous page. Okay. Right. And so from this equation, we can see that U here is 90, but for computing the Peclet number, you can just take the magnitude of this, right? And so we're gonna have 90. Our grid spacing here, since we're working on the same example as last time, is 0.25. And then our diffusion coefficient here is 6. Okay. Okay. And so we compute this out. And so we have 90 times 0.25, and we divide it by 6. And what we get is 3.75. Okay. And so what that tells us is that, our, with the grid the way that it is, we're going to get an unstable solution in the because of the X velocity. Okay. And so in order for our solution to be stable on this grid, and let's assume that, we can't change the grid. So let's say that, we can't just make the delta X smaller. What we're going to need to do is we're going to need to apply upwinding for the X convection derivative. Right. And so we're going to need to apply an upwinding finite difference scheme for this guy. Okay. And since, the velocity here is negative, and so we have a negative 90, the proper upwinding scheme for this is actually going to be forward difference. Because remember, for a positive velocity, what the upwinding scheme that we picked was a backward difference. But for a negative velocity, the proper upwinding scheme is forward difference. Okay. And so now let's apply the Peclet number, compute the Peclet number in the Y direction. Okay. And so the Peclet number in the Y direction is going to be V delta Y divided by K. Okay. And so let's plug in the numbers for this. So our V velocity is 6. Okay. we multiply by 0.25, which is our grid spacing, divided by 6. And what we get is 0.25. Right. And so in the y direction here, what we have is a stable solution. And so we can go ahead and apply central difference for this guy. Okay. Central difference for y convection derivative. Okay. And so now that we know which finite difference schemes that we want to apply for every derivative, let's go ahead and apply these guys to our governing equation. Okay. And so our governing equation, let me write out the whole thing again, is so it's going to be 6 d squared phi dx squared plus d squared phi dy squared is equal to minus 90 d phi dx plus 6 d phi dy plus 3xi yj. Okay. Okay. And so now let's take all of our derivatives here and let's apply our finite difference scheme. Okay. All right. So let me do the diffusion terms first, because this, we did this in the previous example. So for our diffusion terms, we're going to have 6 over delta squared times phi I plus 1, comma j plus phi I minus 1, comma j plus phi I j plus 1 plus phi I j minus 1 minus 4 phi I j. Okay. And so I just, that's just the same finite difference scheme that we applied on the previous example. Okay. And so now we're going to apply, our chosen finite difference schemes for, the convection derivatives. Okay. All right. And so let's do the x convection first. And so for the x convection derivative, remember what we said on the previous page is because we're going to have an unstable solution in x, what we need to do is we need to apply forward difference here, which is our upwinding scheme. It's going to be minus 90 phi I plus 1, comma j minus phi I, comma j. Okay. And so that's the forward upwinding scheme for forward difference upwinding scheme for the x derivative. But for the y derivative, we can just use central difference for this because it's going to be a lot more accurate. Okay. And so we're going to do 6 divided by 2 delta times phi I j plus 1 minus phi I j minus 1, okay, plus 3xi yj, okay. Okay. And so from here, what you can do is you can basically just simplify this expression, right? And so usually what you're going to want to do, just to kind of make plugging things in easier, is you want to take basically everything with a phi, and so all these phi terms, and then let's move them to the same side of the equation. Okay. Okay. And at this point, you can multiply the entire equation by delta or delta squared, depending on whatever is most convenient for you. But for this, let me show you, what it would look like if you, just kept all the delta squareds intact. Okay. All right. And so one more thing that I'll do, just kind of make things a little bit easier for us, is let me change these notations here. Right. Right. Okay. And so it's going to be phi right. Okay. Next, we have I minus 1, which is going to be phi left. Okay. Then we have j plus 1, which is our top neighbor. Okay. Then we have j minus 1, which is our bottom neighbor. Then we have I comma j, which is phi me. Okay. Okay. And so let's go ahead and combine all the common terms together into one side. Okay. And so first, let me do the coefficient for phi right. And so for phi right, what we have is this guy and this guy, right? And so you know, we're going to combine those coefficients, and so we're going to have 6 over delta squared minus, or plus, sorry, 90 over delta, okay? And this multiplied by phi right, okay? Right, so that's the right terms. So now let's do the left terms. For the left terms, we just have 1, okay? And so for the left terms, we're going to have 6 over delta squared times phi left, okay? Right. Next, let's do the top terms. And so for the top, we have this guy and this guy, right? And so this is a positive 6 over delta squared, a minus 6 over 2 delta phi top, okay? And then we have the bottom neighbor, running out of colors here, okay? And so the bottom neighbor is going to be a plus, let's see, 6 over delta squared plus 6 over 2 delta phi bottom. Okay. Then we have phi me, which is this guy right here. And so this is going to be a plus minus 24 all over delta squared. Let's see, minus 90 over delta. This is phi me, okay? And this is all equal to 3xi yj, okay? Okay. And then what we can do at this point is we can just simply plug in all the numbers for this and then get the numerical coefficients and then just apply those to our, you know, to each of the interior nodes, okay? And so let me write out the numerical values and I'll apply this to a couple nodes. And then I think that's all we'll have time for. Okay? And so let's do phi right first. And so for phi right, we have 6 over delta squared. So that's 6 divided by 0.25 squared plus a 90 divided by 0.25. And so this quantity right here is 456 when you plug it all in. Okay. Next, we have 6 over delta squared. So 6 over 0.25 squared. This is 96. Okay. Next, we have phi top. So that's 6 divided by 0.25 squared minus 3 divided by 0.25. This is 84. Okay. Next, we have the same thing, but plus. And so this is 108. Okay. And then finally, we have that term. So it's a minus 24 divided by 0.25 squared minus 90 divided by 0.25. And so this right here is a minus 744. Okay. All right. And so now that we have all of those numbers there, let's go ahead and apply this to a couple nodes in our grid. Okay. And so let's apply to the interior node number 6. Okay. And so first we're going to have, what is it, 456 times the right neighbor. So 456 times phi right. And so the right neighbor for node number 6 is going to be phi 7. Okay. Then what do we have? We have 96 times the left neighbor. Okay. And so we have 96 times phi 5, which is the left neighbor. Come on. There we go. Okay. Next, we have the top neighbor, which is going to be plus 84. And so the top neighbor for node number 6 is phi 10. Okay. Then we have the bottom neighbor. And so the bottom neighbor's coefficient is 108. So we get 108. And then the bottom neighbor for node number 6 is phi 2. Okay. Then we have a 744, right? 744. Yep. Minus 744 phi me. And so phi me in this case is phi 6. Okay. And this is all equal to the source function, which is 3xy, right? And so with the grid spacing of 0.25, this is going to be 3 times 0.25 times 0.25, right? Because that's the physical xy coordinates for node number 6, okay? Right. And so this is 0.1875. Okay. And so that's the equation for node number 6, right? And let's do one more here, just for the sake of completeness. And so let's do node number 11. Okay. And so first we have 456 multiplied by the right neighbor. And so the right neighbor for node number 11 is node 12, right? So we have 456 V12, okay? Then we have plus 96 times the left neighbor. And the left neighbor for node 11 is node 10, okay? So this is phi 10. And then we have plus 84 times the top neighbor. And so the top neighbor for node number 11 is 15, okay? And then we have plus 108 times the bottom neighbor. And so the bottom neighbor for node number 11 is phi 7. And then we have minus 744 phi me, which is phi 11, okay? And then we have the source term. And so the source term is 3 times its xy coordinates. So this is going to be 0.5 times 0.5. And so this is 0.75 right here. All right. And so that's how you do a 2D situation with both convection and diffusion. Okay. And so of course, you know, we've only did 2 of the interior nodes because I'm getting kind of hungry right now and I wanted to eat my dinner. But you know, you can apply the exact same methodology to the other 2 interior nodes that we didn't do, node number 7 and node number 10. Okay. All right. And so that's going to do it for the review. Okay. And so in this review, we basically covered our 2D diffusion equations and 2D convection diffusions. And we kind of walked through 2 examples of, you know, what I would expect you to do on the exam. Okay. And so remember, for the exam, there's going to be no MATLAB. You know, I just want you to basically carry out the calculations and the derivations kind of exactly as I showed here. Okay. And so if you can do this, you know, for a generic, you know, 2D convection diffusion equation with boundary conditions, you know, you're going to be golden for the exam, right? And so best of luck for studying for everyone. You know, if you have any further questions, definitely don't be afraid to reach out. And then I'll see you for the exam next week.